Today, we're going to talk about an element that's so important, so fundamental, you probably don't even think about it. It's the sparkle in a diamond, the energy in your gas tank, and, the very thing that builds you. We're talking about carbon, the element of, well, pretty much everything. So let's kick things off with a little riddle. I want you to picture three totally different things. A diamond, super hard and brilliant, a tank of gasoline, and yourself, a living, breathing person. What on earth could those three possibly have in common? They seem completely unrelated, right? Well, the answer is carbon. Yep, that one single element is the building block for all three. It's the diamond, it's in the fuel, and it's the literal framework of our bodies. So the real question is, how does one element manage to be so many different things at once? To really get our heads around this, we have to start with something that sounds a little weird, what we can call the carbon paradox. Because carbon is absolutely everywhere in life, but it's surprisingly hard to find in the planet itself. I mean, just think about your day, the food you ate, the clothes you're wearing right now, the plastic in your phone, the medicine in your cabinet. It's all built from carbon compounds. It's literally woven into the fabric of our lives. And this goes way deeper than just our stuff. We're talking about every single living thing we know of. From the tiniest little microbe to the biggest blue whale, it's all carbon-based. Life, as we know it, is built on a carbon chassis. But here's the twist. Here's the paradox. For an element that's so critical to life, it's incredibly rare. The Earth's crust, the actual ground we're standing on, is only 0.02% carbon. That's practically nothing. Which leads us to the big mystery, right? How does this super scarce element somehow become the star player, the master architect for all life and for so many things we depend on? What gives? Well, the secret, the magic trick, is all in how carbon atoms connect with one another. It all comes down to a very special kind of handshake, the covalent bond. Okay, so here's the deal. Every atom just wants to be stable, and to do that, it needs a full outer shell of electrons. Carbon has 4, but it needs 8 to be happy, so it has a problem. Gaining 4 more electrons would just be too much for its nucleus to handle, but losing all 4, that takes a massive amount of energy. So since it can't steal and it can't give away, carbon does something brilliant. It shares. And this sharing is what we call a covalent bond. It's not about one atom taking from another, it's about teamwork. 2 atoms link up, they share their electrons, and boom, both of them get to feel like they have a full, stable shell. This bond is strong, it's reliable, and it's the entire foundation of carbon's power. This whole sharing thing, this covalent bond, it gives carbon 2 incredible superpowers. I mean, these are abilities that no other element has to quite the same extent, and it's what lets it build millions upon millions of different compounds. Superpower number 1 is called catenation. It's a fancy word, but all it really means is that carbon is awesome at linking up with other carbon atoms. It can form these really long, stable chains, create complex tree-like branches, or even loop back on itself to form rings. No other element is this good at building with itself. And then there's superpower number 2, tetravalency. Tetra just means 4. Because carbon has 4 electrons to share, it can form 4 bonds at the same time. Think of it like a Lego brick with 4 connection points. It lets carbon build out in 3 dimensions, creating all sorts of complex shapes. So you put those 2 superpowers together, linking with itself and having 4 connection points, and you've got an element that can build an almost endless variety of things. Let's see exactly how that works. Now, these carbon chains can be built in a couple of ways. If all the carbon atoms are just holding hands with single bonds, we call the molecule saturated. It's kind of full up, it's stable, and pretty chill. But if you start seeing double or even triple bonds in there, we call it unsaturated. Those extra bonds make the molecule a lot more reactive, more willing to jump into a chemical reaction. And here's where it gets really cool. You can have the exact same ingredients, the same chemical formula, but get a totally different molecule just by arranging them differently. These are called structural isomers. So take C4H10. You can arrange it in a nice straight line and get butane. Or you can snap them together in a branched shape. Same parts, totally different structures, and they have completely different properties. And as if that wasn't enough, you can also decorate these carbon chains. You can attach little groups of other atoms, which we call functional groups. Think of them like accessories. You swap one little thing out, and you give the whole molecule a new personality. Stick an OH group on there, and poof, you've got an alcohol. Add a COOH group, and now it's a carboxylic acid. It's a total identity change. Okay, so that's a lot of theory. But how does this all work in the real world? Well, let's look at something we all use every single day: soap. The way soap works is a perfect everyday example of carbon chemistry in action. Here's the basic problem of cleaning, right? Most of the grime and gunk we want to get rid of is oily. And as we all know, oil and water do not mix. So how in the world are you supposed to wash away oil using water? It just doesn't work. Well, you need a special kind of molecule, one that can bridge the gap, and that's a soap molecule. It's got a long carbon chain, that's catenation at work, which acts as a hydrophobic tail. That means it hates water, but it loves oil. Then, at the other end, it has a charged head that is hydrophilic. It loves water. So it's a molecule with two totally different personalities. So here's what happens. When you lather up, those little soap molecules get to work. Their oil-loving tails all dive into the greasy dirt, trying to get away from the water. Meanwhile, all the water-loving heads stay on the outside, facing the water. They team up to form this tiny little sphere, a microscopic cage called a micelle, and they trap the oily dirt right in the middle. And that's the whole trick. The micelle has basically gift-wrapped the oil in a water-friendly package. This process is called emulsification. So now, when you rinse, the water can just grab onto the outside of that micelle and wash the whole thing, dirt and all, right down the drain. So, you see, from the molecules that make up our bodies to the ones that clean our hands, it all comes back to those two simple tricks. Just as our source material says, the reason carbon can form this huge variety of compounds is because of its tetravalency, its 4 connection points, and catenation, its amazing ability to link up with itself. We've seen how carbon is just perfectly, uniquely suited to be the element of everything. Which really leaves us with one last kind of mind-bending question to chew on. Carbon is the foundation for all life that we know of. But is it possible that somewhere else in the universe, another element could be doing its job?